Dear friends, in our last video, we connected neural networks concepts to strategies for embodying our new self. However, once we get our nervous system can recognize our new identity, we can help our brain detect its new surroundings, areas of focus, and overall demeanor. We might think of visualization as something from the woo-woo realm, but our imagination works as neurological simulation, emotional rehearsal, and embodied prediction. Are we sure it's not woo-woo? Yes, and neuroscience proves it. According to George Lakoff and Mark Johnson, imagery lives in sensory motor circuits, while Sean Gallagher points out how body schema and mental imagery are interdependent. Studies conducted by Stephen Koslin highlight how the brain uses the same circuits for imagining an action as for performing it. Richard Davidson's research highlights how emotional visualization reorganizes the prefrontal limbic pathways. According to Daniel Siegel, imagery adds new neural firing sequences, which lead to new traits and new identity patterns. In his research, Andrew Huberman further confirmed how imagined visual cues can stimulate or calm the nervous system exactly like real stimuli. Let's think of a dream most of us wish to achieve: to get fitter. Well, studies indicate how visualizing a movement activates 70% of the same neurons as physical execution. The muscles involved show microactivation, which highlights how performance increases even without physical practice. Let's check out the path we will follow throughout this journey. 1. Data preparation. 2. Model creation. 3. Loss function and optimizer definition. 4. Training. 5. Validation. 6. Model saving. 7. Model loading for inference. 8. Deployment or integration. Let's start with data preparation. Datasets, existing or custom. Every deep learning project begins with data. We may either select a dataset that already exists or construct a custom one. When using an existing dataset, several parameters guide our setup. Root specifies the directory where the dataset is stored. Train equals true or false determine whether the data is allocated for training or testing. Download indicates whether PyTorch should retrieve the dataset online if it isn't found locally. Transform and target. Transform. Define how inputs and labels are processed. Features are the inputs used to make predictions. Labels are the outputs the model learns to predict. Features come when we visualize our ideal self as, for example, confident, while labels would be the ease in dropping an elevator pitch. Transforms. In applied deep learning, particularly in computer vision, transformations are almost always involved. Transforms. Compose. Combines multiple transformations into a sequential pipeline. Think of mentally recreating a day in the life of our new fabulous self. What's our sleep routine? What activities do we tick off in the morning? How do we commit to our dream occupation? And how do we spend our evenings? Normalization rescales input values or activations into a stable, standard range. Just like some activities or areas of focus take priority over others when we think of our dream life. Data augmentation, used only during training, increases robustness by creating varied versions of the same data. If we see ourselves as entrepreneurs, data augmentation is like visualizing ourselves in various ways we can accomplish the same goal. Data loaders, batching and shuffling. After the dataset is defined, PyTorch uses data loaders to manage batching, shuffling, and parallel loading. In human terms, a common idea found in Maxwell Maltz, Michael Gazzaniga, and Eric Kandel insists that our nervous system responds to imagined practice as if real. The brain confabulates a coherent self-image by stitching together imagined and remembered signals. That's our dataset. Before training begins, we must specify the device responsible for computation. PyTorch requires clarity on whether tensors and models are placed on the CPU or GPU. Mismatches cause runtime errors. Available options include CPU, the standard processor found in most systems; GPU, highly optimized for deep learning operations. We then move both the model and data to the selected device. GPU stands out like visualizing our ideal self, whereas CPU compiles different facets of our dream identity. GPU is the love story or the revolutionary business, whereas CPU the holidays together or the moment your company is launched on the stock market. When constructing a dataset from scratch, the dataset class must implement three essential methods. Init sets up file paths and annotations. We start with a broad sketch of our identity. Len returns the total number of samples. In how many areas of our life do we visualize changes? It might be just our looks and not our career. Getitum retrieves a specific sample given an index. Does our self-care just mean some me time at the spa or an afternoon in with a good book? We then split inputs and targets. The dataset is divided into X, representing the input features, such as how our dream self looks on paper. Y, representing the target outputs, like scenes of how our dream self behaves in various situations. The neural network must switch fluidly between training mode or how we mentally prepare for a situation such as an event. Evaluation mode, how we actually behave at the event beyond the mental rehearsal. At this stage, we define the architecture of the neural network by creating a class that inherits from nn.module. Common model families include 1. Sequential networks, suitable for simple regression or classification problems. Do I add this activity, habit, or imagery in my vision of an ideal self? 2. Convolutional neural networks, which detect spatial patterns in images and video. What are the look and mannerism you visualize for yourself? 3. Transformers, which leverage self-attention for sequence modeling. Think of starting with the sustainable microhabits, which provide the foundation of whatever image we develop of ourselves, just like workout routines would be when visualizing a fit body. In his book Atomic Habits, James Clear highlights how even a simple statement such as, "I am the type of person who," rewires identity. 4. Autoencoders used for compression, denoising, and dimensionality reduction. It's like starting visualization with our strongest desire. It could be a random day in our dream career or preparing breakfast for the children we're yet to be blessed with. 5. Generative adversarial networks, capable of producing realistic synthetic content. Can we push visualization to the realm of personal branding and think of some extra features, such as entrepreneur and published author or mentor? 6. Graph neural networks, designed for relational and graph-structured data. If our vision of ourselves has a good work-life balance, everything falls into place for long-term fulfillment. The model is composed of layers, parameters, and activation functions. Activation functions introduce non-linearity, allowing the network to learn complex relationships. Sigmoid, suited for binary probability outputs. Do I still see myself acting this way or entertaining these circumstances? Ton, zero-centered, often used in recurrent models. Yes, we start with decluttering whatever we don't like of ourselves. Re-Lu, computationally efficient and widely adopted. Think of the major effect of just one small change, such as waking up early or deactivating our social media alerts. Leaky ReLU mitigates dead neuron issues. The baby steps that seem realistic, such as an hour of dancing in our living room, rather going to the gym. GLU, smooth, probabilistic activation used in transformers. Think of the effect of familiarizing ourselves with a certain setting we associate our dream life with, such as the habit of a periodical lunch at a high-end restaurant. Linear, typically used in regression output layers. We visualize parenthood not only when picking up our children from school, but also when taking them to an amusement park. The forward method defines how data moves through the network from input to output. Once the model is initialized, we need a way to measure how far its predictions are from what we want. This is the role of the loss function. In simple terms, loss tells us how wrong we are, so we know how to adjust. Common loss functions include nn.m, seloss, used for regression tasks, where the goal is to predict a continuous value. Psychologically, this reflects how clearly we can sustain a vivid, continuous vision of ourselves. Can we imagine a full storyline around our desired future, or do we dismiss it as unrealistic the moment doubt appears? Nen-nel loss, used for classification with log probabilities. This can mirror inner conflicts, areas where different imagined identities compete with one another, creating incoherence. Nen-cross entropy loss, the standard for multi-class classification. Our dream identity is rarely limited to one domain. We don't only visualize how we look, but also how we work, love, communicate, and live. Once error is quantified, we reduce it using an optimizer. The optimizer updates the model's parameters based on the gradients computed from the loss. It works as what Elizabeth Stanley states as the window of tolerance, or the range where you can function optimally. When the window is narrow, small triggers feel overwhelming. An optimizer requires model parameters, the values that can change. Psychologically, these are the areas where our imagination still lacks clarity or conviction. Learning rate, how big each update step is. A learning rate that's too high overwhelms the system. Too low leads to stagnation. Notice when doubt creeps in. It's often a signal that the pace of change needs adjustment. And optionally, momentum, which helps learning remain stable by remembering past updates. Just like visualization works best as a coherent narrative rather than disconnected snapshots. Each optimization step follows three phases. 1. Optimizer.0 grad clears old gradients. This is like releasing outdated self-images that automatically surface when we imagine ourselves in the future. Second loss, backward, computes how parameters should change. When current circumstances contradict our vision, we still allow the imagined timeline to influence how we respond. 3. Optimizer.step applies the updates. Gradually, the transition between imagination and reality becomes smoother and more believable. Common optimizers include SGD, simple and interpretable, SGD with momentum, faster and smoother learning, ATOM, adaptive and widely used, especially when the goal is still forming, RMS prop, effective for unstable or changing conditions, ADAGRAD, ADA-delta, useful for sparse or uneven progress. Training progress is often tracked with TQDM, which displays loss, accuracy, and time per epoch. At the end of each epoch, the model is evaluated to ensure learning is moving in the right direction. To prevent overfitting, when a model memorizes instead of generalizing, we introduce regularization techniques. Dropout, which prevents over-reliance on specific neurons. Early stopping, which halts training when improvement stalls. Weight decay, which discourages overly complex solutions. In human terms, we aim for a vision that feels alive and flexible, not rigid or performative. Calling model.train, open parenthesis closes the network into training mode. In this state, dropout randomly disables neurons to improve robustness. Batch norm uses statistics from the current batch to stabilize learning. Each training iteration follows a structured loop. 1. Activate training mode. 2. Reset gradients. 3. Perform the forward pass. 4. Compute the loss. 5. Execute the backward pass. 6. Update parameters using the optimizer. This loop is repeated across batches and epochs, allowing the model to progressively refine its internal representations. Psychologically, this mirrors repeated mental rehearsal. Each time we visualize ourselves responding differently, the nervous system receives new predictions. As Antonio Damasio explains, identity is constructed from bodily sensations, and repeated emotional meaning attached to an image strengthens its credibility. With tools like TQDM, we can observe progress in real time, just as subtle embodiment shifts become noticeable through consistency rather than intensity. For validation and inference, we switch the model into evaluation mode, model.eval. This freezes learning-specific layers. We also use torch.no_grad to reduce memory usage and speed up computation. Evaluation answers a critical question. Does what we practiced hold up in unfamiliar conditions? Performance is measured using task-specific metrics. For classification, accuracy, the proportion of correct predictions. Does the imagined identity match how we actually show up? Precision, how many positive predictions were truly correct? Are we mistaking tension for confidence? Recall, how well all relevant cases are captured. Have we imagined ourselves across enough contexts? F1 score balances precision and recall. For regression, RMSE and MAE, highlighting exaggerated versus consistent deviation from the desired outcome. For computer vision, intersection over union, IOU, how closely predictions align with reality. Are we embodying calm only in rehearsed moments? For NLPBLEU score, which reminds us that occasional slips don't erase overall progress. With training complete and parameters loaded, the model is now ready to generate predictions on new, unseen data. Maxwell Maltz advises that we improve the self-image by feeding it empowering pictures. Furthermore, his observations signal how even emotions such as calmness, poise, or charm can be rehearsed. Imagination should be treated as a tool, not as an escape, Maxwell Maltz points out. Don't imagine what you fear, your mechanism will chase it. To conclude, dear friends, visualization is integrated by our brain to define who we are, what is possible, what we expect, how we respond, what we attract, what we create, what we stabilize into.